Welcome back from the break. So for our next speaker, we'll have Bill from Google who will tell us about state preparation. Please, yes.
Great, thank you. And thank you all for coming back from the break. I know that's the best part of any conference. I'm here today to tell you about a particular technical improvement to the state preparation for a family of quantum simulation algorithms that I quite like, but also more generally, some of the tools that I got a chance to learn about during this project I think may be of more broad interest, and I imagine they'll show up more and more in other places in quantum algorithms, so I hope that some of you all enjoy learning about them as well. But before I get started, I'd like to say some thanks primarily to my co-authors on the paper that I'm speaking about today, but also a number of folks for helpful discussions. The organizers here, I think we're 2 for 2 in beautiful places with QSIM. Let's keep it up. And you all, like I said, for coming back from the break and for your attention. So I should begin by asking, what problem are we trying to solve? And I want to give a little bit of context here since we're addressing a technical challenge with a particular kind of algorithm. And the broad background is a Hamiltonian that's, I'm sure, familiar to everyone here, or if not, we'll be seeing plenty of it today, I imagine. But this is the electronic structure Hamiltonian that in most situations governs the behavior of electrons in molecules and materials and informs the chemistry that we're interested in studying. We might be interested in static properties of low energy states. These are the ones that give rise to most chemistry, but also in some kind of real-time dynamics. What I'm going to share won't be specific to either of these, but they're both interesting tasks. And the kind of algorithms that I'll be talking about are these first quantized simulation algorithms. And the particular kind that I'm focusing on are ones that work in an underlying single particle basis of plane waves. So the states of the electrons, the states the electrons can occupy are represented by some finite set of plane waves. And then you should imagine, if you haven't seen these algorithms before, that we have a register of qubits allocated to each particle in our simulation. And the specific basis states of these correspond to different plane waves that those particles might be occupying. And so you can imagine, if we have a very large number of plane waves, that this can be space efficient compared to alternative representations that might use a qubit for each plane wave, for each basis function. Of course, in order to have a physically valid wave function, a wave function in this formalism needs to actually explicitly encode the fermionic statistics, so that if we think about interchanging 2 particle registers for 2 identical particles, we should pick up a minus sign in the wave function. This will become important later when we think about preparing the initial states for these algorithms, which is why I'm mentioning it now. And it's important to note that the operation that anti-symmetrizes some state is not unitary. It's a projector onto a subspace, and we can perform it for certain initial states, but in general, it's a difficult thing to do. And this will haunt us with the factor of eta later in the cost that I'll talk about. But before we get to that, why are these algorithms interesting? One reason is that they're extremely asymptotically efficient. In particular, the scaling with the number of plane waves, which is the size of the basis set that controls how flexibly we can represent different wave functions, is quite wonderful. We have this end of the, sorry, I feel like I should have a laser pointer and point up there, but I'll have to manage. We have this end of the 1/3 scaling. So this lets us scale to very large numbers of plane waves, potentially beyond what we can treat with even very approximate classical methods. And furthermore, if we're increasing this parameter L, which controls the volume of real space, it's the linear dimension of the space that we're actually capturing, you can see from this expression here that we actually only incur a logarithmic cost. So we can go to very large system sizes, at least in some sense, very cheaply. Furthermore, something that might be important for some applications is that a basis set of plane waves or something else that doesn't encode a bunch of knowledge about the chemistry is unbiased in some sense. So it might give us a chance of avoiding the inductive bias that would come from a very tailored choice of states that our electrons can occupy. But these algorithms also have some disadvantages. One, which I won't say much about today, but is worth mentioning, is that they have very large prefactors, partially from the sophisticated simulation methods required to use them at all, but also there's a large rather large anyway, overhead in the number of plane waves one might require compared to a traditional Gaussian basis set that's probably more familiar from a classical approach to quantum chemistry, at least for molecules. But like I said, this isn't really the focus of the talk. What is the focus is this second disadvantage, the fact that the state preparation for any kind of physically meaningful initial state for these simulation algorithms can be extremely expensive. And what I mean by this is that it's easy to prepare some kind of antisymmetric state, some kind of physically valid wave function, but not a physically relevant one. For example, we might want to start out our simulation in a mean field approximation to the ground state. That's a really reasonable thing to do if we're after qualitative accuracy in some problem. And at least we could do that, prepare the Hartree-Fock state or some other Slater determinant. But even this can be an expensive task as we scale to very large numbers of plane waves. One way of thinking about this is that you could say that all we need to do is to change the single particle basis. And what I mean by that in practice operationally is we'd like to implement some isometry that takes us from the computational basis state, 1, 2, 3, up to eta, to some single particle state that could be a potentially arbitrary state on a Hilbert space of dimension n. So if we could implement an isometry like this on each of the registers, one for each particle, this would complete the task. But this is, of course, unavoidably expensive in general because this V has eta times n free parameters, where eta is the number of particles and n is the size of our basis. Naively, we pick up another factor of eta from having to do this thing eta times. We can do better, it turns out, but it's tricky. And I won't really delve into that particular approach. But also, this isn't even a very interesting initial state. We might want to prepare some richer, better approximation to the ground state or some other physically meaningful state. Okay. So before we actually talk about how we do this, I thought it'd be nice to motivate the talk by showing you sort of a sneak preview of where we actually end up. And so I'm going to tell you a little bit before I jump into how about what the results are when we look at a simple example of preparing the Hartree-Fock state of a water molecule. I haven't explained everything that I've put on this slide, but I've told you that there's this unavoidable eta n cost. And what we're going to see is that by making some additional assumptions, we can go from a cost that's linear in n, which you might think of as 1 million or 1 billion, depending on how accurate we'd like our simulation, to something that's logarithmic in n. There's some other parameters I'll explain along the way, but this is really the big win of our method. I was tempted to title the talk Exponentially Faster State Preparation, but I thought that would be a little too provocative since that's not the exponent that is most challenging to us in quantum computing. However, we do get this nice savings. And furthermore, if we look at the constant factors, which is what I'm showing you on the left, comparing the gray method, which is this something that scales as eta n in a reasonably clever way, with the various realizations, I'll say, of what I'm going to tell you about with different notions of accuracy, we can save orders of magnitude, get an order of magnitude savings or more in the number of non-Clifford gates that we need. And so hopefully this convinces you that there's something worth looking into here. The exact savings could depend on a lot of choices, and I won't say that it's always going to be 3 or 4 orders of magnitude, but there is a real advantage to be had. But where does this come from? Like I said, there's eta n free parameters in that object that defines just an arbitrary Slater determinant, arbitrary mean field state. So we're going to need some additional assumptions to get the kind of savings I was talking about. And the place that comes from in our work is easier to explain and if I start by introducing this notion of a Gaussian type basis set that is perhaps the more traditional approach to quantum chemistry, where we pay a hefty price for discretizing space on a classical computer. And what you should think of is that we're representing the possible states of the electrons as linear combinations of not too many functions that look like this. Some Gaussian times a polynomial prefactor centered at different atoms. And these things are designed specifically to represent chemically relevant low energy states. I won't harp on where they come from exactly, but really the thing that we should keep in mind is that you can get very good accuracy for low energy states with a small number of these things. So our result in a nutshell is that we can efficiently map from a Gaussian basis set to a plane wave basis set in this first quantized representation. And the way that we do that, I won't tell you all of the pieces in detail, but as an outline, you could imagine starting with some of these Gaussian basis functions that I showed you and projecting them onto a plane wave basis. And then we're going to approximate them with a numerical tool known as a tensor train, maybe more familiar to this audience as a matrix product state. And using those approximations, we can construct a matrix product state approximation for each of our individual molecular orbitals, which come from some classical calculation in a way that I'll tell you about. And then we can implement the change of basis that we're actually interested in, this isometry V, using the matrix product states. So I think in some ways the most interesting part of this for me was learning about this notion of approximation with tensor trains that I'm going to dive into a little bit. And so that's where we'll start. But before that, I should probably just recap and explain what do I mean by a tensor train and a matrix product state, and why am I even calling them different things. For our purposes, if you imagine we have some multi-index tensor T with indices S1 up to Sn, a tensor train is a factorization of this tensor into a collection of low-ranked tensors, these A's, with 2 or 3 indices, and then some recipe for summing over the indices. Like I said, these are very familiar as matrix product states if you're coming from a condensed matter physics background. There's a notion of a bond dimension, which is just the largest of those indices that we sum over that's going to control the number of free parameters in this representation. And then the reason I'm differentiating between these objects and matrix product states is partly to give the applied math community that we're going to borrow some tools from its due, because they like this tensor train terminology. But also because it's useful to distinguish between the factorization and the quantum state, which I'll refer to as a matrix product state if we have this factorization. But we're going to use these things in a way that at least I wasn't familiar with before exploring, before trying to explain some numerical results that we didn't understand for full transparency. But this idea is a notion of a tensor train for a function. And the thing you should think about is quite simple. If you have some function f, let's just say it takes one real parameter, you could imagine evaluating it on a grid on some interval a to b, and just think about doing that and obtaining a vector v. And then you could fold v into a tensor in different ways, but you could reshape v into a tensor and then try to represent that tensor with a tensor train. And this might seem like a strange thing to do, but it turns out that a vast number of useful and interesting functions f have very compact representations when you do this. And so the way that we're going to take advantage of this technology is first we take our Gaussian basis function. Here I'm just showing you a sort of one-dimensional component of it because it factorizes anyway into x, y, and z components. We're going to project it onto a finite set of plane waves. And then we can show that we can approximate in the region where those coefficients are non-zero for the values of k, for which they're very far from 0. We can approximate this with a low-degree polynomial. And then what we can do from that is convert that polynomial into a tensor train. And this is a useful thing to do because this has a very concise representation in this tensor train format. So here's an aside on, I want to double check my time, but here's an aside on some work that is not my work, but it's the tool that we really use to make this all make sense, at least analytically, and I think it's some of the most interesting content from at least what I learned in the course of this project. So I want to dive into it, even though we could glaze over it if we were running short on time. And the statement that I'll explain in a little more detail is that a degree d polynomial, if you turn it into a tensor in this way that I described, and you represent it with a tensor train, you can always do this exactly with a bond dimension d plus 1 tensor train. And this is regardless of the choice of A or B or the number of points. And this is a useful thing to do for reasons that we'll see, but but these tensor trains are flexible and have a number of nice tricks we can play with them, including turning them into quantum circuits for state preparation, adding them, multiplying them, all sorts of nice stuff. But why is this true, besides the fact that I have a nice reference on my slide? Well, we can take this tensor that we get from evaluating our polynomial on a grid, and what we're interested in is the minimum bond dimension, but that's really just another way of saying what is the Schmidt rank of this tensor across several different partitionings. So we can try to understand this thing by thinking about matricizing T between, say, the first few indices and the remaining ones. And depending on how we group those things, we're going to end up with a 2 to the q by 2 to the n minus q matrix, where T started out as a 2 to the n, a tensor with 2 to the n entries, and we're looking at different ways of matricizing it. So we could, if we wanted to, convince ourselves that this is an expression that gives you the matrix elements of this matrix M. And as you'd expect, they just come from evaluating the polynomial f at some particular point that depends on j and k and the ends of the interval. And the way I found it useful to think about it is just imagine fixing k to some k bar, and then we could think about a column of this matrix. And what I claim is that we can define a polynomial that depends on k bar such that the entries of this vector, the column of this matrix, just correspond to that polynomial evaluated at these values of j that index the entries of the column. And what you can imagine is that you could take all of the things in that expression above, up here, and just absorb them all into the definition of some new polynomial of degree at most d, so that the only thing left is the j there. And that's, at least in a sense, why we can do this. And then what happens when we look at different columns of this matrix is that we're just evaluating different polynomials on the same set of points. And this is a great situation to be in, because evaluating polynomials on some set of points is a linear map. And degree d polynomials form a d plus 1 dimensional vector space. So the image of this map has dimension at most d plus 1. And of course, these columns are in the image, and so the rank of M is at most d plus 1, which establishes the thing that we wanted. The bond dimension of the tensor train for this thing is at most d plus 1. You can prove similar results for other kinds of elementary functions. We're not going to talk any more about them here. The polynomials are enough for our purposes, but it's a useful thing to know, I think. Okay, so back to the main thread. Instead of just claiming this result about the polynomials, I've shown you a little bit under the hood why it's true. But what does this buy us? Well, we can approximate our primitive basis functions, these Gaussians times some polynomial factor, with a very low bond dimension tensor train. And that's sort of a believable thing, because outside of some window, there's 0, and inside of that window, hopefully they're not too wiggly to capture by a low degree polynomial. And we show that, in fact, that the only parameters that really matter asymptotically for the degree that we need of that polynomial is this L, which is the angular momentum quantum number, or if you will, the exponent in front of the x, or for the x to the L, say, in the definition of this basis function, and some inverse precision. And we depend logarithmically on the precision anyway. So notably, this is independent of the number of plane waves, n. It's independent of L, the size of the simulation box that we're actually working in. And it's independent of gamma, this squeezing factor of the Gaussian. So when we are able to do this for a single primitive Gaussian basis function in one dimension, we can just tensor them together to get the same thing that we need for our 3-dimensional basis function. And the way to think about it is that the tensor train for this function, that's just giving us the coefficients of these basis states k. And that's really the definition of this first quantized representation, is that our computational basis states are supposed to correspond to these different plane waves, and we're supposed to weight them according to whatever state we're trying to prepare. So we can get our matrix product states for 3D basis functions out of this very naturally. And then we can go from primitive basis functions to molecular orbitals. I'm using this term a little loosely here, but what you should think of is just that we have some function of x, y, and z that's a linear combination of not too many, that's this ng here, not too many of these primitive Gaussian basis functions. And we can do this in a variety of ways, but one thing that we can do is we can just take the matrix product state representations that we've constructed for all of our primitive functions and add them together. And we have this nice property from matrix product states that the bond dimension is at most the sum of the bond dimensions of the states that we add. And furthermore, we can numerically round this thing anyway back to some smaller bond dimension if there is a better representation. One thing that I really enjoyed about this project, I think I have time to say this, is that we started out not expecting the scaling to be as nice as it was. For those of you who have used these matrix product states numerically, you've probably seen a lot of times that they just work better than you would expect naively, unless you're trying to compress, say, a random vector, then good luck to you. But they work pretty well just as a brute force numerical tool. And we were expecting something that scaled better. We had some arguments why it should scale better than the worst case, but it turns out that you don't need to understand at first when you're using these things why they work well. You can just try them numerically and find potentially in a very controllable way that you can represent your state or your function or whatever it is with a very compact matrix product state. And this is a really easy thing to try. And I think that this is one of the great strengths of these kind of methods. So anyway, we found that the bond dimension was extremely low, and then we went to ask why, and we've gotten to the story that I'm telling you now. But furthermore, when we're doing this, you can be careful with how you control the error. Either numerically, you can do it carefully as you round and get some guarantees about the error, or in our case, when we're thinking about bounding the error analytically, we found that we just depend on the logarithm of the inverse bond dimension. So we can really make the individual basis functions as precise as we need them to have the overall representation work well. And so what happens then when we actually do this in practice for some molecular orbitals? I showed you kind of a recap overall what the implications are for the cost for state preparation. But this is closer to the why that cost is low. And so I'm showing you here 4 different molecular orbitals, which are these 3-dimensional functions for representative single particle states from a benzene molecule. We ran a Hartree-Fock calculation to get these things in a classical, using a Gaussian basis set, a very classically tractable calculation. And then we get these nice pretty pictures where we show a sketch of what these functions look like in 3 dimensions. They're colored according to the sign. And we just picked 4 of them. There's nothing special about these particular ones. And what I'm showing you here is along the x-axis for these things, the different indices of the bonds in the matrix product state. So, and then on the y-axis, the logarithm of the bond dimension. And for an arbitrary state, what you'd expect is to saturate or nearly saturate this gray line here, this sort of exponentially many parameters that, of course, you would need for an arbitrary state. But what we find is that for these particular functions, when we go and we think about compressing them in this way, for different notions of accuracy here, that I can tell you a little bit more about, we get a dramatic compression, essentially. And this is the reason why the state preparation is cheaper, because we get this compression, and we can go from these matrix product states directly to quantum circuits for state preparation. And one thing I want to point out here, I won't tell you about all of the notions of accuracy. I just like the colors in these plots. But there is a thing that's going on here that's pretty interesting, which is, I don't know if you can see it well on the slide up there, but there's these dotted lines and these solid lines in all of these figures. And those correspond to 2 different classical, 2 different primitive Gaussian basis sets, sort of a very irresponsible small STO3G that you really wouldn't expect to be accurate for any kind of chemical properties, and this somewhat more responsible double zeta basis that uses many more primitive Gaussian functions. And the reason I'm pointing this out is because naively we might think that we're going to scale with the number of primitive basis functions as we start building these things. At least that's the bound that we can prove. But we find that there's really very little dependence. In some places, the solid line is higher. In some places, the dotted line is higher. It turns out that increasing the accuracy of the initial Gaussian basis set that we have started with doesn't necessarily lead to a higher cost here. And I think there's probably more to that story. We can talk about offline if folks are interested. I'm eliding some details that I'd love to chat about as well. There's a question of how do you go from these matrix product states to quantum circuits that has been answered really nicely in different ways in the literature. And you can do it if you have a fault-tolerant quantum computer with no issues in a very efficient way. Also, a question of how do we go from those matrix product states for, say, these chi-j functions, the single particle functions, to the isometry that I told you about. Also standard techniques, but it's worth thinking about carefully and making sure that the errors are bounded. And then maybe most importantly, how do you use this stuff to go beyond single Slater determinants? That is possible if you're interested in some more accurate representation of your initial state, provided that you start with that representation in a compact Gaussian basis set. Then everything we do more or less follows through in a nice way to let you prepare those richer states. I want to circle back now that I've explained a little better what's going on to this overall cost of state preparation. Here I'm showing you a different example. Instead of a water molecule, talking about a Hartree-Fock state of a benzene molecule. Again, I could show you the cost for a variety of choices of parameters here. We're looking at larger and larger sizes of the simulation box and a particular choice of the maximum kinetic energy we can represent. What is the cost of doing that thing using the previous approach that scales is this eta n scaling. It could get quite large as n gets large, of course. And this is something that might happen in practice as you're trying to really resolve the details of some, say, like complicated high energy thing or some dynamics that involve the core orbitals. So there's that cost. And then our method for 3 different notions of accuracy in numerically compressing these matrix product states, sort of across the board when we work out in detail at least the cost for one version of preparing these things in terms of the number of non-Clifford gates that's required, we really get this large constant factor savings regardless of the notion of accuracy that we're using here. I can go into that more offline if folks are interested. I will say that there's a couple of things that are, I would say, unanswered is a better way of putting it than disappointing about the results we were able to prove analytically. And the biggest one is that there's this factor of ng, which is, say, the number of different primitive Gaussian functions that it seems from our numerical results isn't relevant for the particular states that we're interested in preparing, but it's hard to avoid in the way that we were bounding things analytically. So I think that this factor here is actually artificial, and the bounds are too loose. There's also a 2 in front of this number of or in the exponent for this number of particles that we can talk about, but I don't believe in it either. But otherwise, we get this nice logarithmic scaling that we were interested in, and I think that's nearly all that I wanted to share with you. I guess I got nervous and spoke quickly, but maybe that'll get us back on schedule for this morning, so it's not a bad thing. So the overall cost scales logarithmically in the number of plane waves using this approach. The constant factors are rather low, and like I said, the bounds do not appear to be tight. But more generally, beyond the application to this particular problem, which I think is relevant, especially since we're at a conference that's all about methods for quantum simulation. But beyond this particular algorithm, I think there's a useful message here, which is that matrix product states and tensor trains are powerful tools for representing not just the ground states, say, of one-dimensional systems, which I think a number of us are used to, but also amplitude-encoded functions, like these molecular orbitals or other functions of few variables. And one thing which I didn't harp on in the talk, but is a really nice thing to take away, is that their power extends to multivariate functions. Many of you may be familiar with matrix product states in the context of condensed matter, where generally things work great in one dimension, and then they start to work much less great as soon as you go to 2 dimensions. But that's really not the case when you're talking about representing functions of few variables, and that's really why I think ultimately that we were able to get this nice scaling, sort of even better than what we proved analytically. So with that, I guess we'll probably have a little time for questions, and thank you for your attention.
Yeah, we have time for some questions.
Yeah, thank you very much for the talk. So I have a question not regarding to the state preparation, but more about the Hamiltonian construction. So since now we included more terms, like more basis set, then means that we also need to do more times of integral and to get the Hamiltonian. Is that true? And how expensive can it be?
That is true. The nice thing about these first quantized simulation methods that use a plane wave basis set is that you can you can evaluate the integrals analytically by hand. You can also construct the circuits that evaluate them sort of arithmetically, and so the cost, in a sense, scales logarithmically with the number of basis functions. There is a scaling that is where this n to the 1/3 over L comes from in the cost I showed you at the beginning of the talk, that you should think of it maybe as coming from the maximum kinetic energy that you can represent. And so as you increase n, the number of plane waves, if you keep L fixed, you're increasing that maximum kinetic energy, and you do pay a cost for it. It's still the number of plane waves to the 1/3, so you can drive it quite high. But you could also imagine taking, say, a fixed kinetic energy cutoff and looking at a larger and larger size in real space. And this is a reasonable thing to do for molecular simulation, especially because when you use these methods based on plane waves, you're actually introducing this unphysical periodicity to the system. And so you might want to make L quite large in order to suppress the effects of that. And that's actually the place, I think, where our method maybe shines the best, because the Hamiltonian simulation itself scales logarithmically as you make the system size larger. But the old approaches to state preparation would have gotten you this linear cost in that case, whereas we get the logarithmic scaling.
Okay, thank you.
Right.
Good catch.
So I was confused about quantum advantage in the state preparation because you brought in tensor networks, the tensor trains.
Yeah.
And when I saw that, I started thinking, well, maybe you've discovered that you can classically simulate this. Is that?
Yeah. So I think that there's no. Okay, there's a couple of pieces here. First of all, the quantum advantage that you would expect would be in the Hamiltonian simulation or maybe phase estimation that one does afterwards. So we're not hoping for it necessarily from the initial state prep alone. There is a parallel literature, which I didn't get a chance to talk about, that uses, at least much, that uses these kinds of representations to solve all sorts of problems efficiently, just in a totally classical context. And for example, one could find a mean field approximation and do that in a large basis set using this compressed representation. And that could be potentially a really nice thing to do, and there's been some work in that direction. There's also, we like to think about solving all sorts of other problems besides just doing strict, Hamiltonian simulation of a quantum system on a quantum computer. And things like linear algebra or differential equations, there's actually quite a stiff classical competition, I would say, from using this compressed representation to represent multivariate functions and then sort of doing something interesting with it. So it's something to watch out for, but in our case, we can just say, well, we're going to do some quantum simulation after we prepare the initial state.
I see. Thanks.
Yeah.
I don't know. Who's deciding?
Thanks a lot. Maybe directly following up to that, like quantum advantage, and also your comment about how it scales with like the size of the supercell. I guess one context where like classical algorithm might start to like be really costly is like in solids, and also going beyond like you have benzene and you have like a couple of rings, but they are still like very much quasi 1D like stripe geometry. Like, have you thought about kind of applying this method to like a system that are more like extensive and maybe
yes. I think that, so I'm going to speculate, but I think that it's true that you would be able to compactly represent your basis functions for a solid as well. It seems like it doesn't matter that much what functions you pick, as long as they're sort of nice. They often have a really compact representation as tensor trains. You would be paying a cost that scales with the number of particles if you're scaling an extended system and you're imagining adding more and more particles. And so there you might worry that other costs related to that could start to dominate, and it could still be a useful thing to do, but we wouldn't get to say exponential advantage then in any sense.
Thanks.
One last question.
Can I ask? We still have time?
Yeah, just go ahead.
Okay, cool. Thanks for the talk. So I guess my question is that, to me, it seems like you are going for extra steps here. You have Gaussian type orbitals, and then you try to map it back to like plane wave basis functions, and then you do the first quantized fermionic encoding, right? So why don't you just do this encoding on your Gaussian orbitals? And I think you might have mentioned that plane wave has this advantage of not bias, but to me, it seems that in your research, you're still projecting biased Gaussian type orbitals to your plane wave basis, right? So
yeah, that's a really fair comment. I think the original motivation for this was to think about simulating some dynamical process where it would be reasonable to start in a crude approximation to the ground state, and then you'd say like, shine a laser at your molecule and excite things far away from the low energy states. And so the dynamics, you wouldn't want them biased in that way. But maybe the more important reason that you might want to avoid doing these Gaussian orbitals, although one could try to make that method work well as well. But the thing that's really nice about using the plane wave basis set is that you have this very simple representation for the Hamiltonian that lets you get this nice asymptotic scaling, either for the time evolution or for say, the cost of phase estimation. And you are, it's hard to keep that, I think, when you start incorporating more of the basis set into your, a more complex basis set. You end up having sort of more put into the Hamiltonian that you need to account for when you're building those evolution operations.
Okay, thank you.
Yeah, thanks.
Thanks to the speaker.